In this video guide, I want to cover a few more of these rotational equilibrium problems with angles. And in particular, I want to go over examples where you have a beam that's kind of drawn in the downwards direction like that. So these are all very good practice questions to work on. Okay, before we kind of get started with this problem, there are two concepts that I want to quickly review before we get started. And the first concept is breaking down your horizontal and your vertical components. So if you're given like an angle and a magnitude that's kind of coming off in that angular direction, you can find the horizontal and vertical components by using some trig concepts here. So since this angle is adjacent to this side, this horizontal component is really that angular force times cos of 65 degrees. And that means the vertical component is going to be force times sine of 65 degrees. So very similar to the ideas from projectile theory. Also, from your geometry classes, there is a concept that I want to cover regarding angles. So if you have two parallel lines, and this kind of shape kind of looks like an F shape here, there's a concept called corresponding angles, where this inside angle is equal to this inside angle. So these kind of concepts will definitely help us break down this next problem here. Okay, so if I go over this problem here now, we have a 4-meter long steel beam, and it is supported 3 meters from a hinge by a cable attached as shown below. And if the tension of the cable is 150 newtons, we want to find the mass of the steel beam. Okay, so let's go ahead and draw our pivot point first. So a very good strategy is to put the pivot point right against a wall there, and therefore we can eliminate any forces on that wall, and then we can go ahead and find torques at some of the other obvious locations. So if we go ahead and find or draw in our free body diagram, since we're trying to find the mass of the steel beam here, we know this 4-meter long beam has weight, so we'll go to the center of gravity right here, and we'll draw our force of gravity right down, just vertically downwards like that. And we're also given that the tension of the cable is 150 newtons, so we also have a force in this direction, and we'll call that your force tension. All right, so that's your free body diagram so far because we put our pivot against the wall there. Okay, the next thing that you want to do is you want to find all the perpendicular forces, right? So let's go ahead and break down all our perpendicular forces, and then we can figure out where we can calculate the torques. Okay, so if I look at my force of gravity, I do want to say that there's a horizontal component like this, and that means there's a vertical component like that. Okay, and if this is 65 degrees, if I go back to my F shape over here, this is 65 degrees, and that means that this has to be 65 degrees. Okay, so if this green vertical line right here is parallel to this blue line, those are parallel, right? So that means this angle right here has to be 65 degrees. Okay, and then we can now find our vertical component right here. So using a blue marker here, this is the vertical component right there, right? So we can easily find that by using this particular constant right there. So our angle is right here, right? So if the angle is right next to this side there, then we know that the vertical component is going to be Fg times sine of 65 degrees. Okay, so this expression right here will tell us this vertical component right there. Okay, and if I go on to my tension in the rope, this might be a little bit easier to break down because we see this quite often here. Well, here's my horizontal component. I'll call that Fx. Now, I don't need that. What I do need is the vertical component right here, which is Fy. All right, and since the angle is right here, and this is your adjacent side, we know Fy is going to be that angular momentum, or sorry, that angular magnitude, which is 150. So this will be 150 times sine of 40 degrees. All right, so there you go. If I highlight the expressions here in green here, those are the components that we do need to kind of set up our next torque expressions here, right? So using a purple marker here, there's a torque here. This is torque 1, and this is torque 2 there. Okay, now let's move on to our concept of rotational equilibrium here. Okay, so at the pivot, the beam is not moving because we're in rotational equilibrium, and rotational equilibrium means the sum of the torques is equal to 0. Okay, so that literally means that the sum of the torques in the clockwise direction is equal to sum of the torques in the counterclockwise direction. Okay, so let's go ahead and draw another diagram right here just to kind of remind us on what's happening here. So here's a horizontal line, and right here's your pivot point, right? So we do have one torque going like that, so I'll call this torque 1, and we also have another torque like that, we'll call that torque 2. Okay, so number 1, we want to say that torque 1, referencing to the pivot point, this is going in the clockwise direction, right? And that means torque 2, kind of erase this, that means torque 2 is going in the counterclockwise direction, right? Okay, and let's just go ahead and see if we can go back and reference what T1 and T2 are in our diagram right here. So let me kind of erase some of this. Okay, so here are our torques. Here's torque 1 and here is torque 2, right? So that's what we mean on the diagram there. So let's just see if we can further break this down. Now this whole beam right here is 4 meters long, right? So if that's 4 meters long, then this distance right here has to be 2 meters long because it's halfway to the pivot point. And the question also tells us that it's being supported, the beam is supported 3 meters from a hinge. So this distance right here is going to be 3 meters. Okay, so if I go back to my diagram here, I just want to say that this distance right here is 2 meters from the pivot, and this distance right here is going to be 3 meters from the pivot. Okay, so let's go ahead and write in our torques here. So in the clockwise direction, we have torque 1. In the counterclockwise direction, we have torque 2. The general formula for a torque is force times distance. And the general formula for a torque here is also going to be force times the distance. Now, what is the force on torque number 1? All right, when I go back to torque number 1, which is this torque right here, we've established that the force is going to be Fg times sine 65 degrees. So this is going to be Fg times sine of 65 degrees, and its distance is actually 2 meters from the pivot, equals to the next force, which is this force right here in green. And if I go back to my original diagram, I'm talking about this force right here, 150 times sine of 40 degrees. So this is going to be 150 times sine of 40 degrees. And I do want to say that is going to be roughly 3 meters from the pivot point. Okay, yeah, we're almost there. We're almost there, and the question is, we want to find the mass of the beam here, and we know Fg. This is in weight. This is a weight right now, Fg. So if I want to convert this into a mass, we got to write this as mass times the acceleration due to gravity, right? And the acceleration due to gravity is going to be 9.80. So I'll write this as mass times 9.80. Okay. And then from there on, we just solve for this value m here, and then that should finish off this particular problem. Now, just going to a calculator here, if I calculate everything here on the right-hand side, 150 times sine 40 times 3 there, you should get roughly 289.254. And if I go ahead and calculate 9.80 times sine 65 times 2, I'll quickly do that on a calculator right now. 9.80 times sine of 65 times 2, that's going to give me mass times 17.764, and then you can easily solve for mass by just dividing those two quantities. And we'll just grab a calculator here and just do that really quickly, and you should get about 16.283 kilograms. And if you want to round this to two significant figures, 16 kilograms is okay. All right, so just going back to the original diagram here, I guess this beam, if I erase all the colors here, what we're just saying here is that this entire beam right here in green is equal to 16 kilograms. All right, so that's the solution for that first problem. Here's the next rotational equilibrium in this particular problem. So it'd be good practice to kind of make sure you fully understand the previous problem before you work on this one, because as you can see, we do have a beam that's drawn in the downwards direction there. Okay, let's go ahead and start breaking this problem down here first by drawing a pivot point. So I'll put my pivot point right there, and then we'll go ahead and draw a free body diagram. So in this problem, we have a 15 kilogram uniform beam that's 2.4 meters long, and it's suspended from a wall and ceiling as shown. And we want to find the tension in the supporting wire there, right? So if I draw my free body diagram now, there's my force tension like that. Since the beam weighs has a mass of 15 kilograms, we can draw a force of gravity right in the center of the beam. So here's my force of gravity. And there's also this 25 kilogram ball here at the very end, so there's another force of gravity down here, so I'll call this the second force of gravity. Okay, so there is my free body diagram, and we also have our pivot point. And another thing we have to do is we need to find all our perpendicular forces, right? Okay, so our force tension is already at a perpendicular distance from the pivot because of that right angle box. And then I guess we have a horizontal component like that, and then we have a vertical component like that. And we have another horizontal component like that, and we have a vertical component like that. Okay, so let me just erase the horizontal components there. So we want to find the, if I bring up my red marker here, this right here is the perpendicular forces, right? So we want to find an expression for the red lines there. Okay, so we need to go back and understand the concept of corresponding angles. So if this is 65 degrees, just like the previous problem, that means this is 65 degrees, and that means this is going to be 65 degrees. Okay, so we can easily find the component, the perpendicular components. So if I highlight this in green now, in order to find that vertical component there, that's the same thing as FG1 times sine of 65 degrees. And this vertical component here would be FG2 times sine of 65 degrees. All right, so very similar concept from what we did in the previous problem there. Okay, so let's go ahead and set up the rotational equilibrium concept, and that means the sum of the torques is going to be equal to 0. And we'll try to redraw this on a horizontal number line, on a horizontal diagram before we set up our torques here. Okay, so let's just go ahead and write out some more words here. So at the pivot, we want to say that the sum of the torques is equal to 0, and that means the beam is not moving because the sum of the torques clockwise is equal to the sum of the torques counterclockwise. Okay, so let's go ahead and draw a horizontal line here to kind of summarize everything that we found. So here's my horizontal line there. Okay, so we know that there is a pivot point right here. And at the center of gravity, there was a torque going in the downwards direction, so I'll call this torque 1. And at the very end, we had another torque. I'll call that torque 2. And then we had the cable and the wire. We had the supporting wire here, which is around here, so I'll call that torque 3. Okay. So with respect to the pivot point T1 and T2, the two torques in the going downwards, these are going clockwise, and torque 3 is going counterclockwise. Okay, so if I go ahead and set that up, this will be a torque 1 on the clockwise direction plus torque 2 on the clockwise direction, and then we have torque 3 in the counterclockwise direction there. And the general formula for torque is the force times the distance, plus this torque is also a force times the distance, and this torque here is also a force times the distance. And now we got to figure out how to write these forces in terms of their perpendicular components. Okay, so let's kind of erase this, erase that, and erase this. Okay, let's go back to T1 now, which is right here, and let's go back to our diagram here. T1 is really, let me erase this right here. Let me kind of erase all that. So here we are. Here, this is the expression for the first perpendicular force, Fg1 times sine of the angle. And our second torque is going to be Fg2 times sine of 65 degrees. So let's go ahead and plug those in. So this force right here, as mentioned, is going to be Fg1 times sine of 65 degrees. And we're going to ask ourselves, what is this distance from the pivot point, right? So if I go back to my original diagram, the question is, what is this distance here? Okay, well, the entire beam is 2.4 meters long, and the center of gravity is always halfway to the pivot point, right? So half of 2.4 is going to be 1.2. So our first torque is going to be 1.2 meters away from the pivot, plus our second torque. Okay, so let me kind of erase this since we're done with that. So this right here is our second torque like that, right? So what is that distance from the pivot point? Well, that takes the full 2.4 meters, right? So that whole distance is going to be 2.40 meters, right? So we got to take that entire 2.4 meters, and we know the expression for the second force here is going to be Fg2 times sine of 65 degrees, and that's going to be a full length of 2.4 meters from the pivot point. Okay, and now we have our third torque, and the third torque might be the easiest one to kind of calculate here. So we got to find this force tension right now, and that force tension is already perpendicular to the pivot point, and it's 0.8 meters from the pivot point. So this force right here is labeled as force tension times 0.8 meters from the pivot point. Okay, and so we're almost done here. We just need to find expressions for Fg1 and Fg2, and Fg1 is really going to be the mass of the beam, right? So the question does tell you that the mass of the beam is 15 kilograms, so this would be 15 kilograms times 9.80, and then all this remains the same, sine 65 times 1.2 plus, and then Fg2, this is the mass of the object at the very end there, so the cannonball, I believe it was. So this ball right here is 25 kilograms, so its force of gravity change is going to be 25 kilograms times 9.80. And then everything else remains the same, sine 65 times 2.4, and then that's going to equal to the force tension times 0.80. Okay, so you know, a lot of numbers here, but our end goal is to solve for Ft, right? So I'm going to pause the video here and give everyone a few minutes here to kind of crunch out the numbers and find an expression for Ft. Okay, so here's the rest of the solution here. So if I round this to two significant figures, around 870 newtons would be an acceptable answer, or somewhere around 865.98. So these are all very acceptable answers for this particular problem. Okay, so in order before I finish off, let me just go back to the original problem here and erase some of these colors here. A lot going on in this problem, obviously, and what we just found right here is the tension, this supporting wire right here, which was to two significant figures, which was 870 newtons. And if it's 870 newtons, then this whole beam will be in equilibrium, meaning that it's not moving, it's at rest. And I would say anything below 870 would cause this whole beam to collapse. Okay, so that's it for this homework video guide.